Assalamualaikum and thank you Dr. Nur Ain for having time to listen to my presentation today. My PSM project title, Short-Term Aging Effects on Synthetic Hardware Asphalt Binder. First of all, I would like to introduce myself. My name is Fatin Syameera binti Abd Aziz with matric number CF200033 and my supervisor name is Associate Professor Technologies Dr. Muhammad Ezree bin Abdullah. This is overview for today's presentation. First is introduction, literature review. Third is method and materials. Continue with result and analysis. And lastly is conclusion and recommendation. In introduction, I will explain about background of study. Nowadays, the people in the world are racing to make their country successful and not left behind our country Malaysia. This is include the road development. Flexible pavement are usually designed to withstand the load for 10 to 15 years. It is important to explore for technologies and materials that will provide better quality in paving industry. Paraffin waxes are the best and most widely used additive to enhance the quality and flow of binders. There are two types of paraffin waxes, which is bituminous waxes and synthetic waxes. In this project, I will Asphalt, which is one of the synthetic hard wax produced by the industrial that successful in WMA technologies. The synthetic hard wax are finer crystalline structures and longer cover change that contribute to the change of asphalt binder quality through the wet process. It reduces viscosity when added to asphalt and become fully soluble at 120 degrees Celsius. Synthetic hard wax may be used to modify asphalt in order to achieve engineering goals related to viscosity reduction, energy consumption reduction, and environmental sustainability. There are two problem statements in this study. First is the amount, type, and frequency of repeated load by heavy recycle have a significant impact on the performance of pavement. This shows the higher the load, the deterioration also high. Second is premature failure mechanisms such as fatigue and rutting in pavement overlay because of temperature during mixing and compression. This happens because the temperature is hard to control at the site. There are two objectives in this study, which are to investigate the effect of short-term aging on the physical and rheological properties of synthetic hard wax asphalt binder, and second is to determine the optimum percentage of synthetic hard wax to achieve the PG76 asphalt binder performance. For the scope of study, this project is focused on analyze the influence of short-term aging on the physical and rheological properties of asphalt binder containing a different percentage of synthetic hard wax. Synthetic hard wax use is 1%, 2%, 3%, 4%, and 5%. The laboratory tests conducted to determine physical properties and the optimum percentage of synthetic hard wax to achieve the performance grade PG76. The experiment procedure and work method will be based on ASTM and MS. And the experiment was conducted at the Advanced Highway Laboratory UTSM and Center of JKR Crete. This is some of my literature review for this project. From this study, I found that synthetic hard wax gives some good impact to the pavement. Let's move to methodology. This is the flow chart of the experiment. There are two types of material preparation, which is controlled and modified asphalt binder. The process was continued with two conditions, which are unaged condition and short-term aged condition, and the sample was tested according to the list. In sample preparation, asphalt binder and synthetic hard wax will blend to form modified asphalt binder through blending process with temperature 160 degrees Celsius with 2000 RPM in 30 minutes. For short-term aging method, I use RTF40, which is rolling thin film oven test with temperature 163 degrees Celsius for 85 minutes according to ASTM D2872. These are the classification lists for physical properties and rheological characteristics. Next, we continue with result and analysis part. Penetration test conducted to find asphalt binder stiffness or consistency. The lower the penetration result, the more stiff the binder. The control sample has a penetration value of 65.8 dmm, where it is within the range of 60-70. When synthetic hard wax added to the asphalt binder, penetration value become decreased and did not achieve the range. This result showed that synthetic hard wax reduced the stiffness of modified asphalt binder. The softening point test is conducted to find the temperature at which the asphalt binder turns from a solid to a liquid. The standard requirement for softening point test is 48 degrees Celsius to 56 degrees Celsius. The graph shows the control sample with 0% synthetic hard wax has a softening point of 53.2 degrees Celsius, which is still within the standard allowed range. The softening point value increase as the amount of synthetic hard wax increase. As a result, in hot climates, an asphalt binder with a higher softening point is preferred since it cannot flow or melt over its service life. Next, we move to solubility test. The solubility test is to find contaminants in asphalt binder. A minimum solubility of 99% in trichloroethylene is often required by specification for asphalt binder. The control sample has a solubility of 99.7%, where it is within the range and fulfill the specification. All the sample from control to modified asphalt binder meets the requirements of the standard. Ductility test is conducted to find the maximum stretching length of asphalt binder can withstand before breaking. The ductility requirement for asphalt binder 60-70 is more than 100 cm. The control sample has a ductility value of more than 150 cm, which meet the standard. The ductility value drops when the synthetic hard wax has added to asphalt binder. Synthetic hard wax having poor deformation properties at room temperature or below, which significantly reduce the ductility of asphalt binder. The viscosity of asphalt binder at high temperature is an important factor because it indicates the ability to pump asphalt binder through an asphalt plant, cover aggregate in asphalt concrete mix, position to pour the mixture and compact the mixture. Increasing the synthetic hard wax quantity reduce the viscosity of asphalt binder at a given temperature, which are 120 degrees Celsius, 135 degrees Celsius, 150 degrees Celsius, 155 degrees Celsius, and 180 degrees Celsius. The viscosity of all modified asphalt binder at 135 degrees Celsius are less than 3.0 Pascal second. 135 degrees Celsius is because the minimum temperature of viscosity test of performance graded asphalt binder specification. The viscosity of all samples of modified asphalt binder at this temperature meets the superpave binder specification, which is 3.0 Pascal second. Let's move to flashpoint. This test is to determine whether a sample mixture of vapor and air is flammable. A requirement is much larger than 250 degrees Celsius. The control sample has a flash point of 335 degrees Celsius, where it is within the range, and all the sample modified asphalt binder meet the requirements of the standard. Elastic recovery is used to evaluate the recovery ability of asphalt binder after elastic deformation. From the graph, the value increased at 1% and 2% of added synthetic hard wax, while the value decreased when the asphalt was bond with 3%, 4%, and 5%. It became less elastic, had a lesser capacity to absorb stresses, and returned to its original state by adding more than 2% synthetic hard wax. Next is mass loss test, which is test after RTFOT. Mass loss is to determine the volatile component of asphalt binder. The result in more than 1% fulfill the mass loss percentage limit. 4% of synthetic hard wax can slow down the oxidation process on the binders but did not achieve the requirement. all the sample did not meet the requirement. The mixture test is test before and after egging. This test is to assess the binder resistance to rotting. Before egging, it shows that all value of G star over sin delta decrease as the temperature rise. After egging at 64 degrees Celsius, the control binder had a slightly lower than the modified binder and resulting in lower resistance to rotting. However, at all other temperatures, control binder also had a lower value of G star over sin delta. The sample with 4% synthetic hard wax after short egging show greatest value of G star over sin delta at lower temperature, it becoming stiffer, while the traditional binder show less change. This table shows how the optimum percentage of synthetic hard wax asphalt binder is determined. It refers to the performance grade PG76 requirement. The results show none of the sample of modified asphalt binder meet the standard requirement of performance grade PG76. Last but not least, conclusion and recommendation. For conclusion, first is the addition of synthetic hard wax to the modified asphalt binder reduce stiffness of the binder. Second is the addition of synthetic hard wax to the modified asphalt binder produce high value of softening point and will be preferred for hot climates since it cannot flow or melt over its service life. Third, all the samples meet the requirement for solubility test standard. Fourth, ductility decrease with addition of synthetic hard wax modifier, indicating a reduction in performance at 35 degrees Celsius. This study revealed that the use of synthetic hard wax reduced the asphalt binder viscosity and decreased its rheological performance at high temperature, while synthetic hard wax also prevent the short edge binder from breaking at lower temperatures. Lastly is all the samples of modified asphalt binder of synthetic hard wax did not meet the standard requirement of performance grade PG76. This is project recommendation for the future. First is modification can be made by changing the type base of the asphalt binder or increasing the percentage of the synthetic hard wax to enhance the performance to PG76. Second is the synthetic hard wax modified asphalt binder should be tested for long-term egging by using synthetic hard wax in order to determine its performance at lower temperature. Lastly is synthetic hard wax modified asphalt binder should be tested in terms of morphology properties to determine the quality control and performance assessment of synthetic materials used in road construction. That's all for my presentation. Thank you.